Welcome to Nitty-Gritty Talks, and today's topic is alternatives to system-level binary translation. It's been actually several months since the last video, and I really don't like to leave the things just in the middle when the most interesting pieces are just a few miles ahead. If you are new to the series, I would recommend to go to the first video and watch them in sequential order, and I will leave a suggestion somewhere around here. So let's not wait any further and jump straight onto the topic.
What are the alternatives to having system-level translation? We can have virtual machines for simulating like virtual hardware and presenting to the applications something different. So for example, you can run different operating system or even like architecture, like Android emulator, for example, on your Windows machine, which has completely different like a processor and completely different like operating system. Yeah, you can do that. But if we are talking more about the performance, there are a bunch of ways you could go. Actually, all the ways which are listed are hardware related. The first thing you can say is that like workloads have specific like structure, and they all something similar in a way. For example, this like I'm building the application for doing astronomy, which is kind of a lot of trigonometry and everything like that. So why don't I just not take the ARM or x86, any like general purpose system? I would just go for ASIC, and then it would be much faster to execute, which is great. Also, the alternative is to have loop boosters, or actually similar ideas with the different points. So, for example, we have general purpose architecture like x86 or ARM, but we know that there are some codes which are not optimal for this general purpose. We want for those very important codes to have something faster, and the loop boosters is specific piece of hardware which is capable of running loops faster. So, for example, we can imagine the architecture when the code comes to the CPU and it knows that it is a loop. And how do we do that? It's completely another question. So why not offload that to loop booster, which does operate on loops faster than the CPU does, and then like return with the results it has. And the similar thing, why don't we run machine learning calculations on tensor cores or some computational stuff? Because it's much faster. It has much faster, much higher level of parallelism. Or why don't we run on GPU? But for now, we have for GPU, we have to write separate software, and we could imagine it's being implemented in hardware, for example. So, for example, the hardware detects somehow that this workload has very high level of parallelism and sending it to GPU. The problem is that they have completely different architecture and the codes are not compatible. And then you have a dynamic optimizer exactly to do that. So you can integrate that in the flow like this. Also, you have the possibility just to implement hardware optimizations inside the CPU. So you can think of some optimizations which could have been done in software actually, but for some reason they weren't, and CPU understands that it wants the code to be organized differently, and it may do auto unroll. And I believe this is even inside x86 to do auto unroll. And unrolling is basically the optimization, classic compiler optimization. When you do the loop, you make 2 iterations of the loop. For example, you have the loop from 1 to 100 and doing some reads and calculations and stuff. And then you like make body twice as big and having the induction variable step not 1 but 2 instead. And you have the same semantics, but your loop iteration is twice as big, and you can do some optimizations. there. For example, the simplest optimization is that you don't anymore have I++ 2 times. You have only one I plus equals 2. And also you have twice less jumps, which are kind of expensive operation CPU. So yeah, so we do just this on a hardware level. And the downside is that the hardware becomes so much complicated when you do that. So yeah, it's hard to do energy efficiency. It's hard to maintain. It's a lot of legacy. You cannot redesign. That's very, very difficult. So for example, when ARM realized that their hardware is not like competitive with Intel's at the level they wanted it to be, it took them, I don't know, 5-6 years to redesign that. And that was the effort which they started, and they know where they arrive in. And that's not that they took some small steps and that's like evolvement. It is completely different architecture, and that takes very long time to do. For example, with older architecture like RISC-V or anything like that. Yeah, it's quite simple. And having a binary optimizer is a great addition to that. Having simple architecture and offload the difficulty to the software. But it comes at a cost. Yeah, everything comes at a cost.
It's been great to be with you today. Just to make a quick recap, we talked about alternatives to system-level translation, mostly hardware alternatives, and we finish on a thought that although binary translation seems like a good technology, but there is some cost to pay, which we will discuss the next time. And until then, take care and bye-bye.